Since we are talking about microphones, let's look at the wireless option. Why might we decide to use a wireless system as opposed to wired options? Cables are impractical for the freedom of movement. Undesirable because of the optical disturbances. Cables would have to run through any public area. And lastly, cables are not preferred by the end user. A basic wireless signal chain will see the microphone or instrument being connected to a transmitter, most commonly a body pack, but can also exist in a handheld wireless microphone. The source audio signal is then modulated by the transmitter into a radio signal in order for transmitting the signal through the air from the transmitter antenna to the receiver antenna. The receiver then demodulates the radio signal back to an audio signal, which is then ultimately connected to your digital signal processor or mixer. A few things you need to know. Each wireless microphone requires operation on one specific frequency. That frequency must be a legal frequency to use in the country of operation, must not be occupied by any other user, and should be separated with enough distance to an adjacent channel. The transmitter and receiver of a system must work on the same frequency in order to communicate with one another. Two transmitters cannot be used with one receiver at the same time. Two systems operating on close frequencies at the same time can cause interference problems. Wireless microphone systems share their frequency range with other wireless transmission systems like TV stations, radio stations, and mobile phones. Professional wireless systems use the ultra-high frequency range, which lives between 300 MHz to 3 GHz. A major reason we use this is because of the high frequency channel count available to us in an already crowded world of wireless transmissions. Cost-effective solutions do exist in the very high frequency range, but provide fewer benefits compared to those in the UHF range. Interference is caused by radio frequency, which is usually man-made from devices such as other wireless microphones, televisions, and radio stations. One example of interference is when two operators in close proximity are attempting to use two wireless microphones on the same frequency. The strongest signal will always win the battle, forcing the weaker signal to go unheard or cut out. Intermodulation can be generated when two or more wireless systems are working in close proximity to one another and have frequency transmissions that are separated by only a small range. When the two wireless system frequencies interact with one another, they can create unwanted frequencies. These new unwanted frequencies can become a problem when they are of the third order, eating up bandwidth another wireless system may be trying to use. Be aware, intermodulation can occur on both the transmitter and receiver sides of the system. So to remedy this, it is recommended to use only frequencies from a calculated frequency set. We will cover this in more detail in the instructor-led class. Let's start by defining the issues one can experience with the propagation of a wave. We'll use a billiards table to understand the thought process behind propagation. We need for the transmitting signal our cue ball to go to the receiver our red ball. But much like billiards, we must learn to work around obstacles we find in wireless systems. If possible, we should take the shortest path, but as we see, the 8-ball is in the way. In wireless systems, the 8-ball can represent a blocking object like a metal wall preventing the wireless signal from reaching the receiver antenna. The bumpers of a billiard table can act as radio frequency reflectors such as walls and a ceiling in which we are using a wireless system. The pockets of the table represent the radio frequency absorbers. We humans can act as excellent absorbers. If attempting to transmit a wireless signal through an audience, the transmission becomes weakened before reaching the receiver antenna. When placing receivers into an environment, we want a clear line of sight between the transmitter antenna and receiver antenna. Here are some general rules to take into account for receiver antenna placement in an application. It is strongly recommended to have a direct line of sight between transmitting and receiving antennas. Place the receiving antennas at least 5 feet or 1.5 meters away from all transmitters. Place the receiving antennas at least 5 feet away from any big metal object, wire, particularly wire mesh, or sheet metal structures such as walls and ceilings. Do not place the antennas in hidden places such as behind walls. And place the receiver at least 5 feet away from any equipment that may emit radio frequency radiation, such as lighting racks, fluorescent lamps, digital effects units, or personal computers. Finally, let's review the questions as a designer one should ask themselves before submitting the final order for their main system. In which country will the multi-channel system be used? How many channels do you need? Do you know any TV station frequencies that are working in this area? Are there already other transmitters working in this area? What quantity of handheld transmitters and type of microphone heads do you need? What quantity of belt pack transmitters and type of microphones or cable do you need? Do you need any charging units? And for the antenna receiver system, do you have an area plan such as dimensions? Have you drawn in where the system should operate? Where do you want to install the antennas? Where is it possible to run the antenna cable? Where is the position of the receiver? In the instructor-led class, we will explore these questions and many other wireless system solutions.